In this video, I'm going to show you how to solve problems in gravitational force concept. We know that Newton's law of gravitation says the force acting between two masses is given by gmm by r square, where g is the universal constant of gravitation and m and m are the two masses and r is the distance between the center of the two masses. So we know that from this formula you can make out the force is directly proportional to the product of two masses and inversely proportional to the distance square, and g is a constant. Now this constant g is a universal constant. So what it means is the force between these two masses does not depend on the media. Like if you compare this with the force due to electric field. Now this force is the same wherever the masses are in the universe. Some of the important points about gravitational force: this is an attractive force. There is no repulsive gravitational force. It's always attractive. This does not depend on the medium. And one more thing which is not mentioned here is the value of this g, the gravitational constant, is very, very small number. For that reason, the gravitational force between two objects is very small. And these 3 points, they just reiterate the formula. Because the force is directly proportional to the product of the masses, when the mass increases, the force will also increase. And this says when the distance increases, the force will reduce because inversely proportional. When the distance is reduced, the force will also increase. So this force, in general, force is a vector quantity. So you have to keep in mind it has got both the direction as well as the magnitude. Sometimes you will come across diagrams like this where you have got two masses m and m. I have written 1 and 2, and this is the force of attraction due to the mass m, and this is the arrow says the force acting on this mass is towards this mass. Now this is the force of attraction on this mass because of this mass 2. So F equal g m m by r square. And in my previous video we have seen this. We have seen this formula: g m by r square is nothing but the gravitational field strength at a distance r from the mass m. Now if you use the substitute here, you will end up getting the force equals the gravitational field times the mass. So it's worth understanding this formula rather than just memorizing the formula. So I've got an example here. I've got two humans here with 100 kg and 80 kg, and they're separated by a distance of 10 meters. So we are going to find out what is the force of attraction between these two people. Just apply this formula. So substitute the value of g, which is given in a formula book, the value of the first mass, value of second mass, by the distance square. You'll end up getting the force is 5.34 times 10 to 9 Newton. So if you compare this force, this force is so much small, and I don't think the effect of this force on the humans, this is very, very less. And the reason why you're getting such a very small force is just because of this, the value of the gravitational constant, which is 10 to the power minus 11. So I got one more problem here. I got the Earth, and the radius of the Earth, which is given in the formula book. I've got a person 100 kg, which is on the surface of the Earth, and we are going to find what is the force of the gravitational force of attraction on this person. Just substitute the values for g m m by r square, where r is the radius of the Earth and this is the mass of the Earth, and you will end up getting this 981.35. I'm sure you're familiar with this number, because if you multiply 100 by the gravitational field constant 9.81, this is what the value you get. So I got one more problem here, the Earth, and this time the person is 7,000 meters away from the surface of the Earth. So you just have to notice this bit here. Some of the problems, the distance is given from the surface of the Earth. But remember the formula F is equal to gmm by r square. The r, the distance in this formula, is the center to center distance. So here think that this person is on the top of the Mount Everest. Now if you substitute the values of g, m by r square, you can see the force of attraction is just little less compared to the force on the surface of the Earth. Just few more problems to understand the concept. So here I got two masses, two equal masses separated by the distance, or the center to center distance is r, and the force acting between these two is gmm r square. I'm going to increase one of the mass to 2m, and if you apply this 2m and m here, you'll end up getting 2gmm by r square. Now here we know that the gmm by r square, this is the force when both the mass are the same. Now I can say that the force of attraction between these two is 2 times the force when the mass are the same. Likewise, I've increased one mass by 3m, the other one to 2m, and when you substitute here, you'll end up getting 6 times. So keep in mind, the force of attraction is proportional to the product of the mass. Now this product is increased, is a 3 times of that, 2 times of that, so 3 times 2, so the force will increase by 6 times. Now here I have increased the distance by, now the distance is 2r. When you substitute this into the formula, end up getting gmm by 2r whole square, that will be gmm by 4r square, and we know that gm, this is the original force F. Now because of the doubling the distance, the force is reduced by a quarter, so it's F by 4. Here I'm going to reduce the distance. Now the distance between center to center r by 3. When you put that into the formula, you'll end up getting gmm by r by 3 whole square. When you substitute and expand, the 9 will go into the numerator. It goes in numerator, and this bit gmm by r square is the force F, and the new force, the force in this scenario will be 9 times this. Here one more example, just like a mental problem. It's the mass is 4m and here is 2m. The distance is r by 4. You can do this mentally. So product of the masses 4 and 2, 8. So the force is already increased by 8 times. Because the distance is r by 4, this the force will increase by 4 square times. So totally the force will be 128 times F. So again, questions like this could be asked in the exam. So what should be the distance when the force is F by 4? So here it says the force has been reduced by 4. Obviously the distance must have increased by 2, because you know that the force is inversely proportional to 1 by distance square. So when distance doubles, the force will reduce by 4. This is the shape of the graph of the gravitational force between two masses. Because the formula has got 1 by x square, the graph has a shape of 1 by x square. And again, this is the graph when you got two masses, one bigger mass, small mass. The bigger mass has got a bigger force, so obviously it will be further away from the mass where it is 0, and the smaller mass will have a a smaller distance where it will be 0. So shape will be something like this way. So you know that the force is a vector quantity, and you might get problems where you have to use your vector knowledge. So you must know how to do the basic vector addition and how to find the resultant vector. So here I got two masses, equal masses. I've got small mass m here, and this m is in between is exactly equidistant from both the mass. So here you can show the force acting on this smaller mass. You know that the bigger mass is attracting that way, this mass attracting this way. Now if you apply the formula, you get gmm by d square on this side, gmm d square on this side, and both the force has the same magnitude but the opposite direction, so the vector addition gives you a net force of 0. Here I've got 2m here and m here. You apply the force acting due to 2m is this way, and the force acting due to the mass m is this way. So again these two forces are opposite in direction, but the magnitude is, here it's a 2gm by d square, here it's a gm by d square, and when you apply the basic vector addition here, now this is a bigger force, so E minus E2. When you do this type of the vector addition, probably you might have been taught that any force in that direction I can reverse the direction by having the minus E2. So when you add these two, you'll end up getting the resultant force. So here when you apply this vector addition, you get the net force is gmm by d square. A few more examples here. I got two masses and a smaller mass here, and there is a force acting between m and this m and m and this m, and the distance is same from two masses. So if you convert this into the vector representation, so you know that the force acting because of 2m is in this direction, the force because of this m is this direction, and if I put F is equal to gmm by d square, the difference between this and this is the mass. If this force acting between these two masses is gm by d square, and this will be twice of that. So I've written this is F and this is 2F. So this is again a simple a vector addition. You have to find a resultant vector. So I got one more example here. I got a small mass in the center which is equidistant from all these four masses. So I'm going to put probably D, D, and D, and D. What is the resultant force? So you have to represent again by vector. There's a mass here, and this is the force 2F because of the mass 2m, and this is the force acting 2F because of the mass of this 2m, and you will have F because of this and one more F because of this. These two forces are equal in magnitude, opposite direction, they cancel away. These two forces are equal in magnitude, opposite direction, they cancel away. So net force, the net force acting on this mass is 0. Inama? So this is a question from 2017 June. So these two questions are not related to the gravitational force, but they're related to the gravitational field strength, which I covered in my previous videos. So here the question is, what is represented by the gravitational field lines? We all know what is the gravitational field lines, but sometimes it will be difficult to put those understanding into a sentence. So the first thing is the gravitational field. The easy to remember ones is the gravitational field lines. They will tell you the strength of the gravitational field. If they're closer by, if they're very dense, you say it is a strong gravitational field. If they're spread out, you say that's a weak gravitational field. Or if you have a sphere, you know that the gravitational field, when they're close at the surface, you say the strength is more, and when they go away from the surface, the field strength of the gravitational field is less. That's one of the things. And it also tells us the direction of the force acting on a mass. So if you got an object here, and if the gravitational field lines has a direction like this, it means any test object placed here, the force on this object is towards the mass. So the direction tells you now in what direction. The direction on the field lines tells you what direction the force will be acting. The second question is, Figure 6 shows the gravitational field above a small region on the surface of the Earth, suggests why the field lines converge over a smaller area at K. We know that when the field lines are closer by, the field strength is more. And here, if you look at this image here, the field lines have got equal spacing. We call this as a uniform or a constant gravitational field strength. Whereas here, if you compare with this part of the figure, here they're close by. So obviously, the gravitational field strength here is stronger compared to the other part of this image. So you can write at the point K, the lines are closer, so the gravitational field strength is stronger than J. J is the other part of the graph. So this question is from 2018 June. It's a very simple question. You can easily get 1 mark. It's just substituting the values, given values, into the formula F is equal to G mm by r square. So distance between the Sun and the Earth is 1.5 × 10^11 meter. What is the gravitational force exerted on the Sun by the Earth? Sometimes they can also ask you what's the gravitational force exerted by the Earth on the Sun. So you know that these two forces are equally magnitude, opposite direction. Just substitute the value of G, the value of the gravitational constant, and the m and all the three values are given in a formula book. Just substitute here. The distance between the Earth and the Sun is given in the question. And substituting everything, will end up getting 3.5 times so many decimals times 10 to 23. So you just have to round this off, and the answer will be A. So this question is from 2017 June. So this is not again related to the gravitational force, but this is related to the gravitational field, which I covered in my previous video. And we know that the gravitational field G is equal to Gm by r square, where m is the mass of the object and r square is the distance. So here it says a small mass released from rest just above the surface of a Pluto as an acceleration of 0.617. Now if you come across acceleration in gravitational field problem, this is nothing but the value of G, which is also same as the value what would have got by applying the formula Gm by r square. Assume Pluto has no atmosphere that could provide any resistance to motion. Calculate the mass of Pluto. Give answers to the correct decimal places, and the radius of Pluto is this. So they are given the value of G, and you have to find the value of m. But to do that, you have to know the radius of the mass, which is given in the question. You are given the value of the small g, and this capital G you get from the formula book. So when you rearrange this this formula, you will end up getting substitute all the values here, end up with 1.30999, so many decimals times 10 raised to 22. So because most of these all the values given in the question has got 3 significant numbers, so I'm going to round this to 3 significant numbers. You get 1.31 times 22. So this is the answer. So one more easy question. So you'll be comparing forces in 2 different scenarios. So most likely you'll end up having a ratios comparing the forces here. It says the distance between Sun and Mars varies from 2.1 times 10 to the power 11 to 2.5 times 10 to the power 11 meters. When Mars is closest to the Sun, the force of attraction is F. What is the force of attraction when they are furthest away? So there are 2 scenarios. So one is when the planets are closer, which is 2.1, and when other scenario is when the planets are further away with the 2.5 10 to the power 11 distance. So they also given when they're closest, the force is F. So you can, one way of solving this problem is you just have to use the formula. Because in it says a 1 mark question, probably you can do this without actually putting the values here. So the first scenario, I got the force F, which is gmm by the distance square, which is the smaller distance. In second scenario, again gmm by divided by 2.5 10 to the power 11 square. Now they have already given the value of f. Now we have been asked to find the value of f2. These type of problems, always try to get a ratio or fraction or divide one by the other. Because I need the value of f2, I'm going to keep f2 on the numerator. So I'm going to do f2 by f1. Put the formula of f2 here. This formula I can put it here. Put the formula f1 here, and most of the things will cancel away. We'll end up getting 2.1 whole square divided by 2.5 whole square, which is equal to this number, and the answer will be f2 will be, when you cross multiply, f2 will be 0.71 times f, which is this is the answer. So this question is from 2015 June. Now it says two identical uniform spheres, each of radius r, are placed in contact. The gravitational force between them is F, and the spheres are now separated until the force of attraction is F by 9. So here the force is reduced by 9 times. What is the distance between the surfaces of the sphere after they have been separated? So again, it's very helpful sometimes if you can picturize the problem. It says two uniform spheres of radius r are in contact. So I've got two spheres here that are touching each other, and the center to center distance is 2r, r of this radius and r other radius. You know that the Newton's formula says the distance that's in Newton's formula is the center to center distance. So it also says when they're touching each other, the force is F, and somehow the force is got reduced to F by 9. And you know that, from if you apply the formula, you know that when the distance increases by 3 times, the force will reduce by 3 square times, because that is F equals gmm by r square. When r is equal to 3r, the 3r square will give you the 9r square. So obviously what's happening here is the objects must have been separated by 3 times their distance. Now before, the center distance was 2r, now they're gone 3 times apart, so that will be 6r. So what I've written here is, that force is inversely proportional to d square. For having F by 9, you must get the d increases by 3. So distance between the center, which was 2r, now will become 6r. Now when you draw these two spheres with the distance of 6r from center to center, if you take away the radius r and r here, and the surface distance is 4r. So this is the one. So the second problem is related to the density. So here it says a satellite of mass small m is in circular orbit at a height r above the surface of the uniform sphere of a planet of radius r, and the density of this planet is rho. Now what is the force of gravitational attraction between the satellite and the planet? So this is again the easy problem. We have done this type of problems in my previous videos. Just stick with the formula. The force of attraction between any two masses is F gmm by d square, the distance square. The distance between, here the distance is the center to center distance. Sometimes if you don't read this correctly, you'll end up getting the wrong values here. Now this is the planet with radius r. The small mass m is a distance of r from the surface. So you have to be careful when you read this question here. So from the surface it is distance r, but from the center it is the radius r plus one more r here, so it's a 2r distance. So now the distance is 2r. Apply that into the formula. So you get gmm by d square. Now we know that d is 2r, You know the mass of the small mass is m. The big mass, the planet mass, we don't know. However, they're given the radius and the density. You know that the mass is equal to density and volume. Find the volume is a basic mathematics here. Substitute the formula for the mass into the equation, and when simplify, and most of the things will cancel away, you will end up with the g rho pi rm by 3, which is this one. So one more interesting problem from 2016 June paper. This problem is also about comparing two forces. So you'll end up having the fractions or dividing one force by another or one formula by another. So it says two planets X and Y are in concentric circular orbits about a star S. Now S is a star, X and Y are the planet. The radius of the orbit of X, this is r, and radius of orbit of Y, it is 2r, and the gravitational force between X and Y, this is the center distance X and Y, is F when the angle SXY is 90 degree as shown in the diagram. What's the gravitational force between X and Y when they are nearest to each other? So here also they are given the value of the force, and they asked you to find the force when these two planets are nearer. So they're near when the planet X is here and Y is here, and the shorter distance will be r between these two, because from S to Y is 2r, and we know this radius is r, so this distance is r. 2r minus r is r. So you can just apply the formula. So here they are given all these angles, because in order to use the formula you have to know the distance X and Y. You have to know this distance. So to find the distance, you'll end up, you need a right angle triangle, so you can apply the Pythagoras theorem. Now if I take this triangle away, and as shown here, so this is the radius. Now S2 here is r and S2 Y is 2r. We need the distance X and Y so that we can apply the gravitational formula between X and Y, so that you need the distance between X and Y. So apply the basic Pythagoras theorem. You'll end up having this distance here, X and Y is square root of 2r square minus r square is equal to r root 3. Now when the distance between X and Y is r2 root r root 3, the force will be F is equal to gmm by r root 3 whole square. And when the objects are near, that is when the distance between X and Y is r, the force will be gmm by r square. Now we have to find this value, and we know this value. So what I would do is, I'm going to find the ratios. I'm going to divide f1 by f, because I want the value of f. I will try to keep that in the numerator, so that your simplification will be, when you simplify these expressions, it will be easy, just a cross multiplication. So f1 by f. Now f1 is gmm by r square, this is the one, and this normal f is, when they are further away, is gmm by, when you square this, you will get r square 3. When you simplify, most of the things will cancel away. This will go to the numerator. You'll end up having r square by r square into 3, and this will cancel away again. So you will end up having 3. So f1 is equal to 3 times of f. So this one. So we have seen two problems where you're going to compare the forces between two scenarios. Keep in mind, you just have to get the ratios of two formulas, and most of the time it will cancel away and you'll get some answer.